Hello everyone, here's the marking scheme for the 2.6 homework structure and function of the heart. So structure X in the diagram is the SA node or the pacemaker, structure Y is the AV node or atrioventricular node. What happens to the heart as the electrical impulse travels from X to Y? That is atrial systole, or the atria are contracting. Now for part 3, we're to draw arrows on the diagram to show the pathway taken by electrical impulses produced by structure Y. So the electrical impulses from Y, the AV node, they travel down the conducting fibres, down through the middle, and then they go up through the outer ventricular walls, like that. I would probably just put an arrowhead on there as well. Okay. Valve Z is the atrioventricular or AV valve. And during which stage of the cardiac cycle is valve Z closed? That would be during ventricular systole, because it would prevent the backflow of blood up into the atrium as the ventricle contracts. Right, on to question 2. We have to calculate the individual's heart rate. So for that we need to do 60 divided by the length of one cardiac cycle. Okay, so we need to work out the length of one cardiac cycle. Okay, so the three main phases of the cardiac cycle, we've got diastole, systole of the atria and systole of the ventricles. So we can pick any point on the diagram. I'm just going to go from the start of ventricular systole to the end of atrial systole, just before ventricular systole starts again. So we're going to 0.5. So one cardiac cycle is 0.5 seconds. Okay, so we've got 60 divided by 0.5, which gives us 120. So the answer is 120 beats per minute. During the diastolic stage of the cardiac cycle, the atrial muscles are relaxed and the ventricular muscles are relaxed. Diastole is relaxation of the heart. And the valves that will be open and closed in the left side of the heart during ventricular systole, so that's when the ventricle's contracting. So the semilunar valve will be open as the blood is forced out into the aorta, and the AV or atrioventricular valve will be closed, and that prevents backflow of blood into the atria. And then for part D, predict how this individual's ECG trace would change under the influence of the parasympathetic nervous system. So parasympathetic nervous system slows down the heart rate, so that means that the length of time taken for one cardiac cycle would increase. Right, on to some problem solving. So we've got some information about a cyclist. He's pedalling at a constant rate. His work level was gradually raised by increasing the resistance to pedalling, and the graph shows the changes that occurred in his heart rate and stroke volume. So stroke volume is the solid line and heart rate is the dotted line. And we've got to be careful because we have got one of these graphs with the two different y-axis labels and scales. The first question is asking us to use data from the graph to describe the changes that occur in the cyclist's stroke volume when the work level increased from 1 to 7 units. Now, if we look at the graph, we will notice that there are actually two phases to this graph. We have got this one that goes from 1 to 5 units of work, and then we've got a second part to the graph that goes from 5 to 7. So in the answer, you need to include both phases of the graph, right? So for 1 mark, you would say from 1 to 5 units of work, stroke volume increased from 88 cubic centimetres to 140 cubic centimetres. And then the second part is when the stroke volume remains constant. So we would say from 5 to 7 units, stroke volume remains at 140 cubic centimetres. Okay. Right, next one, we have to state what the cyclist's heart rate was when his stroke volume was 120 cubic centimetres. So this is a figure we've got to read off the graph. So stroke volume is 120 cubic centimetres. So I'm going to find us 120 cubic centimetres, and we're looking for the solid line, so we're going along here, right? So we can see just at this point here, 3.5 units of work is when his stroke volume was 120 cubic centimetres. His heart rate is here, so we need to go across and read off the line, and that would be at 102 beats per minute. So we're at 102 beats per minute for that one. Right, for part C, cardiac output is the volume of blood leaving the heart in a minute. It is calculated using the formula shown. Cardiac output is heart rate times stroke volume. Calculate the cyclist's cardiac output when his work level was 6 units. Right. So if we go back up to the graph, I'm just going to rub off all my little things from earlier, and we'll go back to the highlighter. Okay, so his work level has to be 6 units. We have to work out his cardiac output. So here's 6 units. So I'm just going to highlight up this line like that. So let's get his heart rate first. So heart rate is the dotted line. Okay, so cardiac output is heart rate times stroke volume. So his heart rate at 6 units is 140 beats per minute. So 140. His stroke volume is the solid line, so we're going to have to read across to the other scale. So I'm going across this way, and his stroke volume is also 140 beats per minute. So it's 140 multiplied by 140. There we go, I'm just going to change that. So 140 multiplied by 140, which gives us 19,600 cubic centimetres per minute. Okay. So question D, we've got a table showing minimum recommended heart rate that cyclists of different ages should maintain in order to either metabolise fat or improve their fitness. So the first one, part 1, use information from the table and from the graph to determine the work level that the cyclist should maintain in order to metabolise fat. So in this case, we are looking at this column here. Okay. So we've got to go and have a look up at the top to first of all find out how old the cyclist is, and he is 40. So we are looking at this line here. So 116 beats per minute is the heart rate that he should use to metabolise his fat. So we need to work out from the graph how many units of work that is. Okay, so 116 beats per minute. So 110, here we go. So we're looking at this scale over on the right. There's 110, 12, 14, 10, 14, 16. So we're here. And we're going to go along and we are looking for the dotted line. So we're going to go along till we hit the dotted line, which is here. And then we're going to read that down off the x-axis, and that gives us 4.5. So 4.5 units of work. Use information from the table to predict the minimum heart rate for improving the fitness of a 70-year-old. So this time we are looking at this column here. Now a 70-year-old is not included on the table. However, if you notice, every time the age increases by 10 years, the minimum heart rate is going down by 8 beats per minute every time. So if we take off 8 again, we get to 120 for our 70-year-old. Okay, so we're looking at 120 beats per minute. Part 3. As an individual gets older, their minimum heart rate for improving fitness decreases. Use information from the table to calculate the percentage decrease that occurs between the ages of 10 and 60 years. So we're going to need to go back up to the table. Okay, and we're improving fitness. So we're still on the green highlighted column. Okay, and at 10, it's 168 beats per minute. and at 60 it's 128. So the first thing we do is we work out the difference, and that gives us 40 is the difference. We then divide by what it started as, and then multiply our answer by 100, and that will give you your percentage decrease. Right, I will just do that on the calculator. So we have got 40 divided by 168 equals times 100. So 23.8% change. Okay, percentage decrease. Right, number 4. The graph shows how an individual's heart rate and stroke volume changed as their oxygen uptake increased during exercise. Again, we need to be careful because it's one of these graphs that has got 2 different y-axis scales and labels. It's also got 2 lines with a key. We have to state the individual's heart rate when the rate of oxygen uptake was 1.2 litres per minute. So, looking at the graph again, rate of oxygen uptake is 1.2 litres per minute. I'm just going to highlight up that line there. Okay. And we have to look at the heart rate. So, heart rate is the dotted line. So, from the dotted line, we are going to go across. Oops, I'm going the wrong way. Don't do that. Go across there. And we're at this bit just below 100, which would give us 98 beats per minute. And be careful, they've not included units, so we need to do it. Okay, so we're going up there and along on that line. Okay, for part 3, again we're using data from the graph as previously. So we have to use data from the graph to describe how the stroke volume changed as oxygen uptake increased. Okay, so let's look at the graph. We've got to make sure first of all that we are looking at the correct line. So let's highlight it. So stroke volume is the green line. So the green line is this one here, up there. And then it levels off. So, like the previous question, there's 2 main phases to this graph. There's the part where, as we're increasing oxygen uptake, the stroke volume increases. And then we've got this last part here, where the stroke volume remains the same. So, we've got to have 2 sentences, and this question would be worth 2 points. So, we would say, as oxygen uptake increases from 0.2 to 2 litres per minute, stroke volume increases from 88 cubic centimetres, so we're reading off this side, to 156 cubic centimetres. So that's your first point. And then point 2, as oxygen uptake increases from 2 to 2.4 litres per minute, the stroke volume remains at 156 cubic centimetres. Okay. Part 3, state the stroke volume when the heart rate was 110 beats per minute. So heart rate, we are over on the left hand y-axis scale, and we're looking for 110 beats per minute. So 110 beats per minute is here. Oops, I'm a bit squint to there. Okay, so we're going right the way along to the dotted line. There we go. So 110 beats per minute of heart rate is at 1.6 litres per minute of oxygen uptake. So if we highlight this line here all the way up, that gives us the stroke volume here of 150 cubic centimetres. There we go. Just write that in, 150 cubic centimetres. Right, part B, calculate the cardiac output when the rate of oxygen uptake was 2.4 litres per minute. So, cardiac output, if we remember, is CO equals heart rate times stroke volume. So we have got to read both the heart rate and the stroke volume off the graph. Okay, so 2.4 is right at the end here. Okay, this far right one. So heart rate is the dotted line. If we read across from the point there to here, we're at 120. Okay, stroke volume is at 156. So heart rate is 120, stroke volume is 156. Okay, so 120 times 156. 18,720. Now we have to notice that the units of the answer are in litres per minute, and that will be in cubic centimetres, because the units on the graph are cubic centimetres. Okay, so we then have to divide by 1,000 to give us 18.72 litres per minute. Okay. Right, question 5. Which line in the table identifies correctly an effect of the autonomic nervous system on the SA node? So the parasympathetic nervous system releases acetylcholine to decrease the rate of impulse generation and decrease heart rate, so we're looking for C. Question 6. How long does ventricular systole last? Well, during ventricular systole, the volume of blood in the left ventricle would decrease. So ventricular systole starts here and finishes here. So it goes from 0.6 to 0.9, which is 0.3 seconds. The heart rate of this man, so remember it's 60 divided by a cardiac cycle. So we need to work out the length of one cardiac cycle. So we can go from this point here to this point here. So 0.1 to 0.9, so that's 0.8. 60 divided by 0.8 is 75 beats per minute. The volume of blood leaving the man's left ventricle every minute. So we're starting off with 120, 130, and it's going down to 60. 130 minus 60 is 70, so 70 cubic centimetres. Number 7. During a competition, a trained athlete can increase his cardiac output by 7 times. If an athlete has a resting heart rate of 60 beats per minute and a stroke volume of 70 cubic centimetres, his maximum cardiac output is, so again we remember, cardiac output is heart rate multiplied by stroke volume. So the heart rate is 60 and 70 cubic centimetre stroke volume, so that's 4,200. So we have B as the answer. Number 8, mean arterial pressure is a measure of the blood pressure in the arteries. Pulse pressure is the difference between systolic and diastolic blood pressure. We can calculate MAP using the following formula: diastolic blood pressure plus pulse pressure divided by 3. So, if somebody has a blood pressure of 122/80, what is their mean arterial pressure? So using the formula, so their diastolic pressure would be 80, so it's 80, plus their pulse pressure over 3. So their pulse pressure is going to be 122 minus 80, which is 42. 42 divided by 3 is 14. And if we add that on to the diastolic blood pressure, we get 94. So the answer is C. And then number 9, the difference between systolic and diastolic blood pressure is often referred to as pulse pressure. The graph shows the changes in blood pressure as blood flows through the circulatory system. the maximum pulse pressure shown on the graph is, so that would be the point where there is the greatest difference between the systolic and the diastolic. So that's right at the start here. There we go, and 120 minus 80 is 40, so that gives us the answer A.